Hi, thanks for coming today. The reason I'm giving this particular talk is that I've been involved in a spacecraft mission, NASA spacecraft mission to the Saturn system that has been taking data since 2004, a mission called Cassini. And so I'm going to be talking about some of the things that we're interested in about the planet Saturn and what we've learned, what we don't know yet. And I just wanted to mention that John Barbara has been with me this entire time doing a lot of the actual work on things, and also for a few years Joe Ferrier worked with us as well, even though he's now moved on to the CCP project. So I assume that most of you don't spend a lot of time thinking about Saturn, so I figured I'd point out a few things that are worth knowing. First of all, Saturn's a lot bigger than the Earth is, almost an order of magnitude, which means that unlike Earth, it has held on to its light elements, so it's a primarily hydrogen-helium atmosphere, and then it's got trace amounts of other more interesting things, ammonia, water, methane, some of which can condense. At Saturn's temperatures, ammonia and water can condense, and will.
No, it's just
All right. Here is Saturn compared to Jupiter, which is about the same size, a little bit bigger, and you can see they're very different in appearance. Jupiter is a lot flashier, has these things that probably, even if you never paid much attention to the planets, even if you went to maybe the American National History Museum of Natural History, once you probably know that Jupiter looks like this with these alternating bright and dark bands. The bright bands are called zones, and the dark bands are called belts, and Jupiter has this big great red spot that every kid knows about. You can see Saturn, although it's got a banded appearance as well, is just a lot less contrasty, sort of more boring to look at than Jupiter. We'll talk about why in a minute, but that's both a pain in the neck for us and an opportunity.
What's the black spot?
Yeah, does something just hit Jupiter? Is that what that is?
This over here.
Yeah.
Is it a smudge on the screen?
That's what it looks like when something hits.
Yeah, I don't think something just hit. I don't know. I'm not sure what that is. But that was up. And then, by the way, that's not one of our pictures. It's a couple of pictures. And can't tell you, but this is one of our pictures. And this is an artist's thing. This is not. This is a picture of what we would call on Earth OLR, thermal emission to space from Saturn as a function of latitude. And if you can read the numbers, it's around 5 watts per square meter. This is the absorbed sunlight, which is maybe around 2.5 watts per square meter. So Saturn, like Jupiter, is not in global energy balance. It emits almost twice as much as it absorbs. And the reason for that is not because people are putting carbon dioxide into the atmosphere there, but because Saturn has an internal heat source, which is partly just the heat left over from the time of its formation in the solar system, but also partly because this hydrogen and helium deep in the interior of Saturn are slowly differentiating from each other gravitationally because of the differing molecular weights. And as the helium separates out and sinks to the bottom, that gravitational energy is converted to kinetic energy and then ultimately to heat. So Saturn is still cooling off just as Jupiter is, and so it's emitting more radiation than it absorbs. And as you can see here, there's no equator to pole temperature gradient the way there is on Earth, and that's because this internal heat source, by the way, which produces, we believe, a convective interior deep atmosphere of Saturn and Jupiter, redistributes the heat pretty efficiently. And so unlike Earth, where everything is, or a lot, is driven by the equator to pole differential insulation and heating and temperature gradient, on Saturn and on Jupiter, you don't have that. You have this interesting hemispheric difference. When Cassini got to Saturn, it was southern summer, and I'll show you what I think might be responsible for this difference in a little while, but it's not crucial to the rest of the talk. Okay, so if you have any experience observing Earth, you don't know how good you have it until you try to observe a planet like Saturn. Earth is ideal for actually sensing the entire atmosphere because partly clear, partly cloudy, so you can observe the surface, you can observe the lower troposphere, you can observe the upper troposphere, and then you can even get above the clouds and observe the stratosphere. From satellites, you can see mostly everything that you need to see, unless you're an ocean person and you want to observe the deep ocean, then you've got a problem, and then you have something in common with us on Saturn. Saturn, as you saw in the previous slide, is overcast, and that means we can't see through the clouds down to where we care about seeing. And so a lot of what we know about Saturn is about its stratosphere and upper troposphere, and about down to the what we would call the middle troposphere on Earth is about as far as we can get, which means we have to make inferences about a lot of what's going on at the depths that we don't actually see. On Earth, it's pretty easy to put a satellite into orbit and see the entire planet at once. We do that all the time with geostationary satellites, for example. But Saturn, being an order of magnitude almost bigger, means that if you want to see a significant fraction of it, you've got to stay far away, but then you don't resolve things too well, and so there's sort of a sweet spot in between where you can resolve things about as well as you want, but you still only see one region on the planet. And so if you want to do global stuff, you have to mostly produce mosaics of images, and that's another pain in the neck. As you all know, Saturn has rings, which is beautiful, but for those of us who want to study the atmosphere, they just get in the way, make it impossible to see parts of the planet at times. That's a problem we don't have on Earth. This maybe is the most important thing, is that, again, we don't know how lucky we have it when we're trying to understand Earth. Earth is a strongly forced planet. It's relatively close to the sun, lots of absorbed energy, lots of need to get energy out to space, several hundred watts per square meter, and as a result, we've got pretty vigorous weather, lots of things going on in the atmosphere, and you can take a satellite image of the Earth on any day of the year and probably see most of the phenomena that we care about going on in the atmosphere. Okay, you'll see the background waves, you'll see the thunderstorms, you'll see evidence of the Hadley cell, and so on and so forth. You don't get that on Saturn. Saturn's far away. We're only talking about a couple of watts per square meter. We're talking about a thick atmosphere that takes a long time to respond to perturbations, and a cold atmosphere, which also makes it very slow to respond to perturbations. And so on that weakly forced type planet, the things that are actually determining the general circulation and the climate aren't happening all the time. They happen once in a while. And so you've got to observe it a lot before you finally see something of interest. Okay? And then, of course, on Earth, the largest, despite all the satellites, the largest, most authoritative record of what's going on in Earth's atmosphere comes from our radiosonde network all over the world, even though it's more dense in some places than others, and that's perhaps the most invaluable piece of information we have about Earth's atmosphere. So far, we haven't been able to get the sounding data yet from the Saturnian Weather Service, and so we have to make do just with the satellite data to learn things. Huh? Need to send money, that's right. And to be serious, there has never been an in situ sounding of Saturn's atmosphere, not even one. Okay, so everything we know is from remote sensing. And finally, one other contrast, there are no guns on Saturn. As far as we know. So, here's what we think the vertical structure of Saturn's atmosphere looks like. Here's a temperature profile for you, just to orient you with the tropopause here, in maybe not too different a place than Earth's tropopause is. This is an old figure. Here are actual temperature profile reconstructions from an infrared instrument that is based down at Goddard. So you can see where the real tropopause is not too much different place than Earth's tropopause. It's about 100 millibars. And here's what we think is going on below. If you just do thermodynamic chemical modeling of an atmosphere that starts with the equivalent of a solar composition and Saturn's temperature profile and so on, and figure out what should condense, then you come to the conclusion that there should be water condensing down deep, and then above that there should be ammonium hydrosulfide, NH4SH, and then there should also be ammonia condensing in the upper troposphere. We don't for a fact know that most of this is true. It's hard to identify the things that actually are condensing, and this is true, by the way, of Jupiter as well as Saturn. One thing that's different about Saturn is that it has this upper tropospheric haze that has a visible optical thickness of about 10. That's why Saturn looks so much more bland than Jupiter when you look at pictures of it, because of visible wavelengths you're seeing mostly this upper troposphere haze. And again, that can be aggravating because down below where all the stuff is condensing and releasing latent heat, especially we think water, we can't see there most of the time, at least not directly. Although we can try to see down as far as we can. Interestingly, this haze, we don't know what it is yet, even though it's the thing that we can see directly with our instruments. The early assumptions were that it was sort of the equivalent of thick ammonia cirrus clouds, small particle ammonia ice clouds, but people who have done spectroscopic observations of Saturn have never been able to find an absorption signature for ammonia ice, and so that makes people scratch their heads. Other people have suggested that there are hydrocarbons, because remember there's methane in these atmospheres, and then when UV light hits methane, it breaks it up and you can start to form higher order hydrocarbons, and there's a much optically thinner stratospheric haze that people think is associated with these higher order hydrocarbons, and some people think that those hydrocarbons, some of which may absorb sunlight, are settling down and coating perhaps ammonia ice particles, but all of it is just speculation at this point. The one thing we know is that this haze must be absorbing, because if you look at temperature profiles on Saturn, one way in which they differ from Earth is that you don't just have this sort of monotonic decrease of temperature up to the tropopause and then an increase in the stratosphere. Instead, you have this bump, this little almost temperature inversion just below the tropopause. And you'll notice that it varies with latitude. Again, Cassini got to the Saturn system in southern summer, so the southern hemispheres where the sunlight is strongest, and that's where this bump happens to be the strongest, and it gets weaker as you move toward the equator and into the northern hemisphere. And so whatever this haze is, it must have some kind of absorbing component to it.
Tony, why does the curve end at 273 on Saturn? Did you explain that already? Did I miss that?
Oh, which one? This one?
Yeah,
this one here? So we don't know how much water there is on Saturn. If you take a solar composition atmosphere, an atmosphere whose relative abundances of the elements are consistent with what we know about the sun, then you should get water condensing somewhere close to 273. Okay? We don't know how much water there is. Many people think that water is enriched relative to solar abundance on Saturn and on Jupiter. That would put the base of the water cloud much lower, maybe closer to 300K, depending on exactly how enriched you think it is. And so wherever this diagram came from, it's an old diagram. I think they were probably using the solar abundance assumption, but you know, just take that with a grain of salt. We don't actually know how much water is there, except for the fact that we don't think that Saturn can have less water than a solar composition atmosphere, because we do see evidence for thunderstorms on Saturn that we think can only be driven by water, and that indicates that there must be some pretty decent abundance of water on Saturn. So it could be super solar, but we don't think it's subsolar water abundance. I'll show you pictures of those later.
So it's great. It's a reducing atmosphere, right? There's no oxygen, there's no ozone. So what are the chief absorbers in the stratosphere?
So I think methane is the main thing. So so you have a stratosphere because of methane gaseous absorption, and then if you form higher order hydrocarbon particles, particulates, just as we for example know occur on Titan, then that can add to the absorption as well. But probably methane is the primary absorber there that produces the stratosphere. Okay, and you say it's a reducing atmosphere, mostly H2, and as a consequence, what oxygen you have is locked up in water. Okay, just as what nitrogen you have is locked up in ammonia, rather than things like N2O or NO2, stuff like that. Okay. All right. So here's what Saturn looks like at a couple of different wavelengths. So our camera, our main camera on Cassini, has 24 different filters on it, observing different parts of the spectrum from the UV somewhat into the near IR. And our two favorite filters for observing Saturn are these two, which we call CB2 and NG2. This is a spectrum of Saturn through the most of the shortwave part of the spectrum, and basically we like to, so you know, traditionally you take pictures of planets out here in the visible, and that's mostly what the Voyager mission did back around 1980, 81 or so. But the problem with visible wavelengths is that they really can't see through that haze, and so you would like to observe at longer wavelengths so that you can at least partly see through the small particle haze down to something deeper, because the longer the wavelength you look at, the lower the optical thickness of that haze becomes. And so we observe in several different what we call continuum bands that are in between methane absorption lines. And so here is the one that we'll be talking about during this talk. CB2, where you can see Saturn is bright at that wavelength. Adjacent to it, you've got a very strong methane absorption band, one of 3 that we have filters at that we call MT2, and these are sort of our workhorse filters. With CB2, we can see at least partly, not completely, but partly down through the haze to some of those lower clouds, whatever it is they're made of. We're still not sure what we're actually seeing there, but whatever they are, we can see them, and you can get some, especially with some manipulation of the images and image enhancement, you can get some nice feature contrast there that allow you to say some things about the dynamics. And with the methane absorption filter MT2, the weighting function for that stops in the upper troposphere because of the absorption of methane gas around the altitude where the upper troposphere haze occurs, and so Saturn has a very different appearance in that filter. So again, it's a pain in the neck to have this haze here, but we can exploit the presence of that haze in these clouds below by imaging at 2 different wavelengths that are better at seeing one versus the other, and therefore it gives us some altitude discrimination. You can think of this as being not completely unlike the standard technique of imaging the Earth from geostationary satellites in a visible and an infrared filter to give you some. The CB2 filter is something like having a visible filter where you're mainly looking at how bright and optically thick the clouds are. And the MT2, although the physics is different, is telling you something about altitude discrimination, although that works a lot better on Jupiter than it does on Saturn. But that's the basic idea, is to try to look at 2 altitudes and be able to see things going on at different heights, and maybe that tells you something interesting. Okay, here is what the mean zonal wind profile of Saturn looks like. And associated with these bands, there are alternating eastward and westward jets that are very fast by Earth standards. The Equatorial Jet is especially fast. It's around 400 meters per second, and it varies with time for reasons that are still to be understood. But if you go to higher latitudes away from the equatorial region, once you get into the 30s of latitude, then you start to see this alternating eastward and westward jet progression. And these are somewhat connected to the albedo features that you see on Saturn. This is an eastward jet here, and this is a westward jet here, but it's different on Saturn than it is on Jupiter. There's a different association of albedo with winds. On Saturn, the eastward jets tend to be in these kind of narrow, dark channels, and the westward jets tend to be in these broader, more splotchy features. On Jupiter, there's a little bit of different association of those, which again makes Saturn a tougher nut to crack. But anyway, so the question we'd like to know dynamically is, well, why are these jets there, and what maintains them? And so some more specific questions are, again, Saturn's very deep atmosphere compared to the Earth. And so are the jets deep? We can only see them at the top. Do they actually extend far down into the atmosphere? Is the forcing for them deep or shallow? People have often thought in planetary science that if the jets are shallow, then the forcing for them must be high up. If the jets are deep, then the forcing for them must be deep forcing. But actually, any of you who work on Earth's stratosphere know that we've come to appreciate in recent years the idea that you can have downward control of the troposphere from the stratosphere. So just because you see something happening in the troposphere doesn't mean that the stratosphere is not influencing it or even causing it. And so you have to worry about that as well. What's the driver for these things? Is it being primarily driven by this internal heat source and this convective interior, this convective turbulence that's going on? Or is the radiative heating at the top of the atmosphere explaining what we see? Where does the energy itself come from? That is, what physical process? Is it just turbulent dry convection, or are there other instabilities going on like we see in Earth's atmosphere, where we have moist convective instabilities, we have baroclinic instability, in some places we might have barotropic instabilities, what's going on Saturn, and then why are the jets the width that they are in latitude, and how does it decide to get the energy up to that particular scale? Those are all questions we'd like to know the answer to.
Tony, is there any topography?
Topography?
Is there any topography?
No, so it's believed that Saturn has a core, a rocky core in the middle that might be actually much larger than Earth, but still small compared to the size of Saturn. That is believed, and this will become important for at least one or two slides later on. The molecular hydrogen and helium mixture, as you go deeper into these much higher pressures, starts to become more of a metallic, electrically conducting fluid. And early on, it was believed that that represented sort of a very distinct phase transition that would make it impossible for flows to extend below that transition point, that metallic hydrogen area that surrounds whatever rocky core it has would then be electrically conducting and would be the seat of the dynamo processes that produce Saturn's magnetic field. These days, people don't think maybe it's such a discontinuous thing, and so that it just sort of gradually changes character as you go down. And that's a question that plagues people who think that the processes controlling what we see at the top are actually forced down deep. They don't know actually what to do with that, which of course what it does is it enables them to just make any assumption that they want to get their model to work. All right. The association of cloud features with dynamics on Jupiter is very clear. Jupiter has these alternating bright zones and dark belts, and here's a wind profile from Jupiter that we made from the same instrument on Cassini, because we flew by Jupiter on our way to Saturn, but this general aspect of Jupiter has been known for a long time, and you can see where you have cyclonic shear, like, this doesn't work too well, but where you have cyclonic shear, in those dark shaded locations, those are where you have the dark belts, and where you have anticyclonic shear, those are where you have the bright zones, and it works like a charm on Jupiter to associate those things. Over here is Saturn, and you can see that the association is not as clear. I mentioned that the eastward jets tend to just be in these kind of narrow dark lanes, and the westward jets tend to be in these kind of broad splotchy things. But again, that's because I think we're looking at this upper tropospheric haze on Saturn, and we're looking down deeper on Jupiter to something that's maybe more directly connected to where the dynamics is being driven. So that's an assumption.
Tony, where does the color come from? So why are things dark and bright?
Good question. So I'll get to that in a second.
Since you just mentioned cyclonic, did you say anything about the rotation relative to Earth?
Oops, I didn't. I had a slide that said it, but I didn't say it. There it is. So Saturn is a very rapidly rotating planet, 10 hours and 39 minutes, thanks, Jimmy. So about 2.5 times faster than the Earth. And so we expect Saturn to be in a quasi-geostrophic dynamical regime. The difference with respect to Earth is that unlike Earth, where you have a relatively statically stable atmosphere, on Saturn and on Jupiter with these internal heat sources, we expect them to be highly convective in their interiors and over a large depth of the atmosphere to have near adiabatic lapse rates, although there could be stable layers in various places, for example, associated with condensation of water and things like that. But rapidly rotating planet.
So, what's the reference point for the rotation rate?
We don't really know, and the problem is that we can't tell how the magnetic field is really rotating, because the magnetic field is too close to being lined up with the pole, and so there are radio periodicities that one can detect coming from Saturn, from which they derive this rotation period. But some people think that is not a reliable indicator of what the rotation period actually is. And furthermore, some of those methods that they've used to indirectly infer the rotation period have given a result that changes with time, which tells you it's probably wrong. And, okay.
Can you pick a bunch of points, like some in the eastward going and some in the westward going just, and analyze a bunch of photos, get a rotation period for each of them, and build some kind of statistics, try to get the answer?
So I mean, that's essentially, what you're doing here is you're taking that reference and then calculating motions that you measure relative to that, assuming it's the right reference. If you do this for Jupiter, then you find out that the jets more or less, except for the Equatorial Jet, forget about that, but they more or less center somewhere near zero with approximately as much westward motion as eastward motion. Try to do the same thing for Saturn, you'll see that there's this bias towards eastward, or we would say prograde motion on most of the planet, and that's one of the things that has made people suspicious that the rotation period that we assume for Saturn isn't quite the right rotation period, but it's an unsolved problem for Saturn that remains. And so you'll find papers in Nature and Science, I guess mainly in Science, I think, about different possibilities for the rotation period of Saturn that don't differ dramatically. We're talking about differences of 5 to 10 minutes in rotation period, not hours. And so I don't think anyone suggests that it's going to be in a fundamentally different dynamic regime, but there is this question hanging out there of whether most of the motion on Saturn is truly eastward, or whether there really is more like Jupiter, more of an alternating eastward and westward motion. Don't know the answer to it yet. And of course, the other thing about the other planets besides Earth is that we know orders of magnitude less about them. So all of these good questions we just don't have answers to. We learn what we can. There are a couple of important length scales that are worth knowing about when you study the dynamics of a planet. If you think about an atmosphere, there is resistance to motion in the vertical due to the static stability of the atmosphere, as characterized by the Brunt-Weissel frequency. And there is resistance on a rotating planet to motion in the latitudinal direction, as measured by the strength of the Coriolis force, as represented here by the Coriolis parameter, F. And so just kind of dimensionally, you can argue that the ratio of kind of the typical vertical extent to the typical horizontal extent of an atmospheric phenomenon should have a ratio something like the strengths of these two retarding, if you will, forces, F over N. And if you then solve for the length scale that satisfies that, you come up with this length scale called the Rossby radius of deformation. This length scale actually pops out of linear baroclinic instability theory, sort of one of the first things we knew from modern dynamical meteorology about the Earth's atmosphere, is that mid-latitude storms tend to have sizes, horizontal sizes, that are roughly in accord with the Rossby radius of deformation, and this just again pops out of baroclinic instability theory. And baroclinic instability turns out to be one of the candidate mechanisms for what drives the jets on the Jovian planets. And so it's interesting to know what this is. The problem with knowing what it is that this, on Earth, we know the static stability very well, because again, we're launching soundings all the time. We know exactly what the temperature profile looks like. On Saturn, it's hard to know what this is, and because this depends on how much the lapse rate of the atmosphere deviates from the adiabatic lapse rate, and since in a convecting atmosphere the lapse rate is very close to the adiabatic lapse rate, all we know about N on Saturn is that it's very small. We don't know exactly how small, so we can't really put a good number on this, except to say it's probably a lot smaller than the width of the jets themselves. Okay. So unlike Earth, where to a first approximation, this kind of simple idea roughly explains how big mid-latitude storms are, on Saturn it doesn't tell us that, but it may tell us the spatial scale at which energy is being injected into the atmosphere if baroclinic instability turns out to be an important process. There's another length scale that's important called the Rhine scale. If you look at the vorticity equation and you look at the terms of advection of vorticity, there is a relative vorticity advection determined by the shear and curvature of the flow. That's represented by this term, where zeta is the relative vorticity, and then there's a planetary vorticity beta associated with how F, the Coriolis parameter, changes with latitude. For very small scale motions, relative vorticity is more important than planetary vorticity. Okay, and for larger scale motions, the planetary vorticity, the rotation of the planet, becomes much more important than the relative vorticity does. If you ask at what spatial scale these two things become comparable to each other, you come up with another length scale given by this expression here, where U is the typical strength of the horizontal wind, and that's called the Rhine scale. And the idea, for example, if we take the example of mid-latitude baroclinic waves on Earth, we have an eastward jet in the mid-latitudes. Actually, there are two different eastward jets, but for now, let's just think about one of them, the so-called jet stream, right, that we all hear about, that is baroclinically unstable with warm air to the south and cold air to the north in the northern hemisphere. And Rossby waves are being generated along that jet stream and propagating westward away from it. And if you look at how the displacements of air go, then those displacements of air are such that when air is moving toward the center of the jet, it is moving faster than average. When it's moving away from the jet, it's moving slower than average relative to the jet itself. And so that induces, averaged over the whole wave, a net transport of momentum into the center of the jet that makes it stronger and accelerates it, and then decelerates it away from the jet core. And if you ask what is the spatial scale over which that adjustment occurs, it is about equal to this scale, the Rhine scale. All right. And so some people say that actually for Earth, it's not the deformation radius that is the characteristic scale that determines the size of our low pressure centers, but it's actually this Rhine scale that results from the nonlinear interactions. There is, the energy is injected at this scale, and then the turbulence, there is an inertial cascade up to larger scales of the turbulence that finally gets to this scale, which explains how broad our weather systems actually are. People actually still argue about this, and there have been a number of papers in the literature recently, because actually on Earth, the deformation radius and the Rhine scale are fairly close to each other, and so some people think that there really is a turbulent inertial cascade from the Rossby radius up to the Rhine scale. Other people say, no, that's not actually happening on the Earth, and people are still arguing about this today. Meanwhile, there's another scale, a guy named Boris Galperin, who says that, well, actually the Rhine scale is not necessarily the important thing for the physics. People used to think, because of this relationship here, that basically turbulence would cascade upward in scale until it got to this scale, and then Rossby waves would take over from turbulence, and you couldn't make things any bigger than that. And that's why the jets on the Jovian planets, for example, had the separation that they did. But what Boris has done is make arguments that suggest that no, the fundamental place at which turbulence gives way to Rossby waves is at this scale here, where this epsilon is the rate at which the energy that's injected at the smaller scale into the atmosphere, the rate at which it is shifting to larger scales, and beta is the same beta we had up here. And again, he's made arguments for the relevance of this to Earth. On Earth's atmosphere, again, all these three length scales are about the same, and so you can take your pick as to what you think is actually going on, although he thinks it might be a marginally important thing in the oceans on Earth. But on Jupiter, the nice thing is that the radius of deformation is probably a lot smaller than the Rhine's radius, or I'm sorry, the radius of deformation is a lot smaller than the Rhine's radius, and there's plenty of room in between for another length scale, and he argues that actually this is the main thing that's happening on the Jovian planets, is that turbulence is cascading up in scale until it gets to this scale, and that's the scale at which the jets are forming, and that they only get to the observed scale of the Rhine scale when the things that are forcing them balance out with the things that are dissipating them, because that sets the magnitude of the wind, which is what this Rhine scale depends on. And so he claims it's a forcing dissipation balance that explains the magnitude of the jets that we see. But again, everybody argues about this stuff. Nobody knows what's right. Okay, so why does Jupiter have the color? Why do the Jovian planets have the colors that they do? Partly we don't know the answer to that. Partly people had ideas about it. So early planetary observers, way before the spacecraft era, around the time that I was born, couldn't help but notice that although we don't think of Earth as a banded planet the way we do Jupiter, actually Earth is a banded planet. And if you look, this is a global Earth image, composite put together from MODIS data. And of course, you know, right? We have the ITCZ, bright clouds, and then we have the subsidence subtropical, the Hadley subsidence regions of the subtropics, which are dark because there aren't clouds there, not because they're inherently bright, but because of the absence of clouds. And then you go to higher latitudes and you get into the mid-latitude storm tracks, and then you get another band of bright clouds. And so early observers of Jupiter said, gee, well, Jupiter probably is just like the Earth. It's got these bands of cloudiness in darker areas where it's not cloudy, and this just has to do with things like the Hadley cell. So they concocted this very simple idea that zones are bright because these are bright equal cloud, right? And so zones were regions of rising motion where something was condensing out and making bright clouds. Belts are darker because that's places where air is subsiding, evaporating clouds, making it dark where you just see whatever's left over after the clouds go away, and that explains why it has this banded appearance and why you have bright and dark. And coincidentally then, if you imagine that this is caused by a Hadley cell type circulation, then you have air rising here and then, for example, in the northern hemisphere, drifting poleward toward the belts where it's sinking. Coincidentally, you have a Coriolis force that deflects you to the right and forms eastward or prograde motions there, which explains then Jupiter's eastward jets, and you have the opposite happening here, which produces the westward jets. So everything that you see on the Jovian planets is just associated with these mean meridional circulations and the Coriolis forces on them that then just determine the eastward versus westward jets. Nice, easy model, and this goes all the way back to the early 1950s. Actually, this first idea was first published by Hess and Panofsky the year before I was born. 1951.
But if that would be true, why would that be darker? Because there's still...
Because of the absence of strongly scattering material like bright clouds. Why is Earth darker in the subtropics than it is?
Yeah, but we see the surface, but they
Right.
don't see the surface.
Right. So but eventually something is going to absorb the sunlight, and it's just not bright clouds, right? So hydrogen eventually absorbs things, whatever trace gases. Methane itself absorbs shortwave radiation, not too much in the visible. They never got as far as saying exactly what would explain how dark it is. There are various ideas about some of the colors on Jupiter. For example, one of the big ideas is, so some people say there might be sulfur compounds that give things their color. Some people talk about phosphine, pH3, that comes up from deep in the atmosphere that produces reddish colors in places, perhaps in these belts. But since you don't know exactly what it is that you're looking at, when you're looking at the belts, it's very difficult to assign something definitive to it. The more definitive thing they were willing to say is that the bright things were actually clouds made out of one of those condensables or all of those condensables, whether it was water, ammonia, or ammonium hydrosulfide, and that's why it was bright. And so the opposite of bright is not bright. Okay. But to this day, we don't truly know everything about the colors. But this is what the dynamical picture was assumed to be. Okay. So anyway, so with Cassini, you can actually ask whether you can test this hypothesis, and the way you test the hypothesis is to try to figure out whether the air is really rising in these zones or anticyclonic shear regions. Well, just as on Earth, measuring large-scale vertical velocity is a very difficult thing to do, but we know that on Earth, in the places where you have large-scale upward motion, on average, those are places where you tend to get moist convection. We know that we have things on both Jupiter and Saturn that are expected to condense and you have this convective interior, and so it's natural to ask, do you see the equivalent of moist convective clouds on the Jovian planets, and do you see them preferentially in zones where people say they should have rising motion? So we go looking for convective clouds on the Jovian planets. It's a lot easier to do on Jupiter because on Jupiter we don't have this thick tropospheric haze, so we can use the continuum band and the methane band, just as Bill Rosso uses visible and IR to define deep convective clouds on the Earth. It's harder to do on Saturn, but just in the continuum band alone, you do see a lot of these little bright features that pop up here and there that evolve very quickly in time and then go away a short time later. And so if we assume that those are convective clouds, and for Saturn we basically just have to assume that that's the case. On Jupiter, we can actually associate things like this with higher convective cloud tops because the methane band is more sensitive to height variations there than it is on Saturn. But on Saturn, we just have to assume that the same is true as on Jupiter. And if we just count these things and ask where they appear on the planet, then here's what you get. So on Jupiter, first of all, here is the wind profile. Again, these are the belts and these are the zones. Here are the number of what we identify as deep convective clouds, and there's a very obvious correlation of the deep convective clouds with the albedo patterns and the wind shear on Jupiter. In particular, convection tends to occur in the cyclonic shear regions, which are the belts. That is exactly the opposite of this picture. This picture says the zones, the bright places, are where the convective clouds should be, in the belts where are the equivalent of the subtropics on the Earth. We're seeing the convective clouds almost exclusively in the dark places. They're little bright things that pop up in the midst of an otherwise dark background. And the bright stuff, the zones, we see no evidence for anything that looks like convection in those areas. So we think that the old idea is completely wrong.
The clouds on Earth being bright is a function of them being composed of a very specific set of molecules. Has anybody just in a lab tried to make a cloud of the substances that are on Saturn just to see whether they're bright or dark when they form?
Okay, so ammonia, ice makes a bright cloud, makes a whitish cloud. Ammonium hydrosulfide makes a bright cloud also itself, and of course water makes bright. So all the major things that we expect to condense all would make bright clouds. And as far as convection goes, only water is there in sufficient abundance to have to release enough latent heat for deep convection to be plausible. But for these broad cloudy areas on the Jovian planets, a lot of people just assume that what they're seeing is ammonia ice, and the problem is we haven't spectroscopically detected it yet, so we don't know what's wrong. But all the major things we expect to condense should be bright in their pure form, if not contaminated by absorbing materials like sulfur, like phosphine, like hydrocarbon haze settling out of the stratosphere and stuff like that. Yeah, so we do know that all those are bright.
But Tony, couldn't that kind of asymmetry between shear and convection and observation bias related to thicker or opacity of the anticyclonic regions?
And so,
which might be consistent with that
right, and
whole picture.
and so we worried about that in the beginning, and what you can do is that you can do it objectively rather than just eyeballing it, and you can make, say, the equivalent, let's say the Saturn or Jupiter especially. It's a lot easier again to do on Jupiter, but you can make the Jupiter equivalent of the ISCCP optical thickness cloud top pressure histograms, and you can find the corners of the histogram where certain extreme cloud types exist. And what you can do is you can at least compare the things that we are pretty sure are convective clouds in the belts and ask where they reside on that diagram, especially in the continuum brightness. And then we can look at the same distributions for the zones. And those things are brighter, that the things that we identify as convective clouds are brighter than anything we see in the zones. And so if there was convection going on in the zones that was anywhere near as deep as the convection that we see going on in the belts, then we would see it. Maybe we wouldn't see it so well visually unless we really enhance the images, but certainly in a plot of the brightness in the methane band, continuum band plane, we would see it popping out as something that was higher and brighter than other stuff, at least brighter than other stuff. And the stuff in the zones is just not as bright as the stuff that we identify as the convection in the belts. And so we're interpreting that to mean that that stuff is just not there. There's nothing as bright.
Did you see the belt?
So well, we don't know how deep we see in the belt, but what we know is that where there's a convective cloud, we don't see very deep at all. So that's in a deep convective cloud, that's where the methane band intensity would be at the bright end, because there's very little absorption of gaseous methane above it because it sticks up so high. So it would be bright in the methane band and bright in the continuum band. And the most important thing though is that in the continuum band, which is a pretty straightforward thing, there's nothing as bright in the zones as the bright stuff that we see in the belts that we call convection. So it could be that there's convection in the zones that's shallower and therefore not as bright. You can't rule that out. But there's nothing going on in the zones apparently that is as deep as the stuff as we see in the belts. And so that's how we decided that it's probably not an observational bias for us.
And can that more shallow convection, if it's more spread out and more long term, can that explain? I mean, can that
So
hold
shallow
up the same
convection could
picture?
very well be going on, and we probably wouldn't see it at all.
But can that explain the same
No, because
traditional
because
view?
it wouldn't extend over the depth that we need to explain the circulation. So we're basically we're looking to test a hypothesis that the Jovian planet circulation that we see in the clouds and winds is sort of an analog of Earth's tropical circulation, where you have a Hadley cell that is about as deep as the deep convection goes.
Mm-hmm.
So shallow convection may very well be there, but it can't drive this whole troposphere depth
Yeah.
returning circulation.
So the white stuff that you actually see there is not high enough for that.
It's not as high as the deep convector stuff. It's higher on average than the stuff
Mhm.
that is in the belts, but it's not higher. It's not as high as the occasional little deep convective storm.
Yeah, but that could be a special case or so. But I mean, it could be that the white belts, that is more of a continuous convection going on there that can hold up the traditional story.
It could be, but it has to be significantly shallower than the stuff that we see going on in the belts.
Yeah. Okay.
Okay, so
Yeah.
that's the difference. You can't say that there's an absence of convection in the belts. All we can say is that it can't be very deep
Yeah.
compared to what we see in the belts.
Mm-hmm.
And so therefore there can't be as much latent heat release associated with it. There could be a whole lot of shallow convection going on.
Yeah.
Okay. On Saturn it's actually tougher to do than on Jupiter, but there's still some association of the convection with cyclonic shear regions. It's not as good as we see on Jupiter. Sometimes we actually see convection on Saturn that's right in the middle of the eastward jets, even occasionally in the westward jets, and so the association isn't quite as good on Saturn, but still there's more convection in the cyclonic shear regions than anyplace else.
Why does that graph not go to the North Pole?
Oh, so this was a graph made early in the mission when we were mostly observing the southern hemisphere of Saturn. We were in southern summer, not doing much observing in the northern hemisphere, a lot of which was in darkness. Okay, so a more updated version of that would have the entire profile. Yeah, it's just it was an old figure that I took.
And these short-lived storms, that's hours, days, what is that?
So these things that we're talking about are mostly short-lived storms, hours to a couple of days. I'll give you an alternative in a little while. Okay, so again, this is the old picture that people had from the 1950s of what the Jovian planets look like. We actually think the opposite thing is happening, and that the place where you do get deep convection on Saturn is really in the belts, not in the zones, and that the mean meridional circulation is going the other way, so that instead of being an analog to Earth's Hadley cell, it's actually an analog to Earth's mean meridional circulation in the mid-latitudes, a Ferrel cell. Okay, and the Ferrel cell is driven by eddies, mid-latitude eddies on Earth, and so if there really are Ferrel cells on Saturn, then we have to ask, well, what are the eddies that drive them?
So you have superrotation on Saturn.
Maybe. We don't know.
So that wind profile.
We don't know what the rotation period is. So certainly at the equator we do.
Right. Okay. So you have equatorial superrotation. So that's assigned to the eddies very strong.
Those eddies are, yeah. And there's a question of what the eddies are. And there's some thinking maybe that the eddies that are responsible for the equatorial certainly the equatorial superrotation, no matter what you think the rotation period is. There's a prograde equatorial jet. The eddies responsible for that may not be the same eddies that are responsible for the mid-latitude jets. Maybe. Not sure. So there are a variety of theories for what creates the jets on the Jovian planets. They fall into roughly two classes. People who wishfully would like to believe that they don't actually have to deal with the whole depth of the Jovian planet atmosphere, which is computationally extremely difficult to do, and that you can just imagine the Jovian planets as sort of more rapidly rotating versions of terrestrial planets with shallow atmospheres, where all the action's happening at the top, and maybe you have to change a lower boundary condition, make a couple of other assumptions about things. That's something that Mike Allison has thought about a lot over the years. But there are a lot of theories that try to explain the Jovian planets in terms of that. And then the question is, if you're going to have shallow circulations, then what's the driver for those eddies that are creating those circulations? And so, again, there are people who have done models where radiative heating does the job. This is Junjun Liu and Tapio Schneider at Caltech, although actually Tapio has now moved to Switzerland, who have an idea like that. Leon and Schoeman at the University of Arizona also believe in a baroclinic instability type thing, only here the baroclinic instability is actually driven by the condensation of water in convective clouds rather than by sunlight. There are other ideas that don't invoke baroclinic instability at all. Just imagine that moist convection occurs, and because you've got divergence at the top of a convective cloud in a rotating atmosphere, that's going to produce a vortex, an anticyclonic vortex, and the via 2D turbulence ideas that will eventually just grow up to the jet scale and produce the jets there. There's a whole different class of theories that say, no, we think that the Jovian planet atmospheric circulations are fundamentally deep. This idea was first promoted by someone called Fritz Butze at UCLA in 1976. And he imagined that on the Jovian planets, when you have a deep rotating fluid, that convection organizes itself into columns that are parallel to the rotation axis. And you can actually produce this phenomenon in the laboratory under the right conditions. And he imagined then that you would have these kind of cylinders of convection that were parallel to the rotation axis, and a series of these cylinders that were concentric with each other would wind up producing, as a surface manifestation, transports that would produce jet surface that looked like those on the Jovian planets, but that the depth of this circulation would only go down to the boundary of this liquid metallic hydrogen core that we believe exists on the Jovian planets. And so there would be a range of latitudes where those processes were occurring, and then there'd be a discontinuity in a range of higher latitudes where those processes were not occurring. People have tried to make this work numerically. It's very hard to do these models. You have to make a lot of simplifications, like a Boussinesque fluid. You have to make things viscous enough for numerical stability, much more viscous than a real atmosphere would probably be. You're making some assumption about the size of the region where the flow is excluded from in the interior. None of these things can really be justified, but people make assumptions. And what a group of people, a guy at University of Alberta named Ritz Heinkel and Jonathan Arnoux at UCLA have decided is that actually if the region where you can't have any flow extends out to about 0.85 to 0.9 of the total radius of Saturn, so that these deep convective cylinders are actually restricted to a fairly narrow range of latitudes from about plus to minus 35 degrees, then these convective cylinder transports within this region here will give you momentum transports up to the surface that produce this equatorial jet on Saturn, and that poleward of that you would have a different regime of flow that was a lot shallower, and that would explain why you have these alternating but much closer together jets at the higher latitudes. And here's a result of the zonal wind field from their numerical simulation, and it produces things that really just look very much like Jovian planets, which is great, except that they've got a whole bunch of free parameters that they have to select in just the right way in their Boussinesque fluid to make it happen. So the relevance of this to the actual atmosphere, who knows? We try to, whoa, what happened with that? Okay. We've tried to actually measure eddy momentum fluxes to produce a constraint on things, and you can't see this very well for whatever reason, but this is a plot, if you could see it, of the Eddy momentum flux. Basically, we track features in the images and try to look at little blobs of cloud and see how they move from one image to another and measure a wind speed from that. And then we produce zonal mean winds, and then we produce fluctuations about those zonal mean winds, U prime and V prime, and correlate them and see whether we can actually measure the Eddy momentum flux. This is a plot of the Eddy momentum flux as a function of the latitudinal shear of the mean zonal wind. And for those of you who know anything about the atmospheric energy cycle, the rate at which eddy kinetic energy is being converted into mean zonal kinetic energy is proportional to the product of U prime, V prime, and du bar dy. So if they're positively correlated, as you can probably still see they are, even though you can't see the details of this, then that tells you that in the northern hemisphere, for example, the eddy momentum flux is toward the north in places where the wind is strengthening toward the north, that is, it's into the jet, and likewise on the other side of the jet. So from both sides, the eddies seem to be fluxing momentum into the jet, and that's actually a similar situation to what we see in baroclinic storms on Earth. And there's just a picture of that going on, and this is sort of a real image analog of that schematic diagram of the Rossby wave that I showed you earlier, with this chevron-shaped morphology being indicative of eddy momentum transports into the center of an eastward jet.
Tony, what is the time resolution of the images you can look at?
So we get various time resolutions, and what we use for this, though, is we use images separated by one rotation. It's a trade-off between two different things. The shorter time separation you use, the more accurately you can do things because the cloud doesn't change shape so much, but on the other hand, the smaller the distance it moves, which means the accuracy with which you can measure the wind is degraded. The longer time you wait, the more accuracy you have in the displacement, but the less accuracy you have because of the change of the shape of the feature. We typically use images separated by one rotation, but people sometimes do things with images separated by an hour or a couple of hours. That's like the 10 hours and 39 minutes. You can't go, there's a time in between, kind of 1 to 2 hours and 10 hours that you can't do because the features just pass over to the night side on the planet. You don't see them anymore.
Tony, what's the overall length of your record?
So it started in 2004, mid-2004, still going today, but we're not looking at Saturn all the time, so we have periods of time for a couple of months when we observe Saturn a lot, and then other periods of time when people are doing other things on Cassini and we don't get to look at all. So we have a bunch of observing periods throughout the years that we get to see, and we're still accumulating images.
What kind of orbit is the satellite?
So the satellite is in these highly elliptical, it started out in these highly elliptical orbits in which they are using the propulsion system to change the orbit continuously and move it all over the place, from orbits that have large apoapses to orbits that have small apoapses, to orbits where the apoapsis is on the day side, a small phase angle, to things on the night side, in the ecliptic plane, out of the ecliptic plane, and that's because they have to satisfy the desires of not only the atmospheric scientists, but the geologists who are interested in doing close flybys of all the small satellites that surround Saturn. They're interested in the science that the ring people want to do, so they have to get up out of the ecliptic plane to look down at the rings. And there are all of these magnetospheric and space physics people who want to be on the night side watching all the charged particles go by and the magnetotail and all of that stuff.
When you say one rotation, you mean rotation of the satellite or the planet?
One rotation of the planet. 10 hours, 39 minutes, 24 seconds.
Are you able to just happen to have the satellite back to that point one rotation later, it's doing all these crazy orbits?
Well, when we're, okay, so one orbit may be, so the orbits we like to do our science would be orbits that might be several months long, and especially out near apoapsis, the satellite is moving very, very slowly. So you sit there, and when it comes back a rotation later, the satellite hasn't moved very much in 10 hours, 39 minutes, and 24 seconds. So we can pretty reliably then come back and see the same piece of real estate over and over again, because we're doing our business far away where the satellite's not moving much relative to the time of one rotation of the planet. Okay. So I think let me just skip ahead because we have to end here. This is what happens if you composite all the wind velocities in in all of the eastward jets and westward jets that you see in the two different filters. So here's the one that sees deeper, where we've got strong eastward jets. At higher altitude, we've got a weaker and broader eastward jet, which tells me that the eddy processes that are focusing the jet are stronger at the deeper level and weaken as you go upward, which would argue against the Riemann-Schneider radiative driving scenario, which has to take place at higher altitude on Saturn, we think. And indeed, consistent with that, when we look at the eddy momentum fluxes, the eddy momentum fluxes are much larger, deeper, and much weaker higher up. And that's only going on in the eastward jets. In the westward jets, there's virtually no difference in altitude in both the zonal wind and the eddy momentum flux behavior. So we think that the jets on the Jovian planets, or at least on Saturn, are being driven below the level that we see, and that the best guess for that is that baroclinic instability driven by the latent heating is going on. But there still is not a completely satisfactory idea about that. Just one other thing to say, and that is a curious thing, that is a curious and very impressive thing that happens on Saturn but does not happen on Jupiter. We see all these little convective clouds all the time on Saturn, but every once in a while a giant convective cloud comes along. So this one came along in 2004 at 35 degrees south latitude. It appeared here. This is a false color image that John Barber made so that you can kind of see the height discrimination, but this bright area here is the top of the convective cloud. And this thing lasted for weeks. The radio and plasma wave experiment people detected radio emissions that are called Saturn electrostatic discharges from that, which we think are indicative of lightning. When this thing was present, happened again in 2006. This time when it happened in 2006 at the same latitude, 35 degrees south, we were able to detect lightning flashes on the night side, but only at 35 degrees south latitude over a period of many years. Then in late 2010, all of a sudden another gigantic storm broke out, only this time in the northern hemisphere, at what latitude? 35 degrees north. This storm lasted for 6 months. And this time we were even able to, I don't know if you can barely see it, but we were even able to make a lightning detection on the day side right in the middle of the storm. So we're pretty sure that these are organized and long-lived convective storms that are lasting for months. And during the whole Cassini period, they've only occurred at two latitudes, 35 degrees south and 35 degrees north, which just coincidentally happen to be the latitudes in the deep cylinder theories at which you make this transition from one type of flow regime to another flow regime. Why that would be of relevance to that particular result, why it would produce convection, I have no idea. It's just hard to escape the coincidence that these two very dramatic things we've seen on Saturn happen to have occurred at only those two latitudes during the entire mission. Okay, oops. So I'll stop there. I missed it. So you put up my final picture. Thank you. There. This has nothing to do with the talk, other than the fact that it's Saturn. It's just the prettiest picture that I think we've ever taken of Saturn. This is Saturn eclipsing the Sun. So you can see, looking back at the inner solar system, you can see the sun barely peeking out here, and you can see the rings. Illuminating the night side of Saturn. So this is porn for people who are into scattering phase functions. Okay, and the only other thing to point out is that little dot there is the. So I love that picture. Anyway, thanks for staying with me today and listening to something that you're not usually interested in. Appreciate it. Thanks. More questions? Yes, that's more questions.
So you talked about the lifetime of these superstorms, but what is the lifetime of a regular storm?
So most of those little things that we see, they might, we see them once and we come back one rotation later. In other words, 10.5 hours later, they might be gone, or they might still be there for another 2 rotations or 3 rotations, but no longer than a few days. Usually it's just those 2 big things that seem to have lasted for extremely long times.
You must look at star occultations and things like that going through. Do you get profiles that you can use?
So we aren't doing that ourselves. There are plenty of people who've done those occultations, those stellar occultations from Earth, in fact, to do soundings of Saturn's atmosphere. More to the point, you can have occultations, okay, of the spacecraft itself, and so as the spacecraft itself disappears behind Saturn, it's sending its signal, radio signal toward Earth, and you can look at how that's attenuating as it goes down, and you can derive temperature profiles from that. The temperature profile I showed you was not from that, but that's one of the things that people do on these missions. They make those occultation profiles. You have to know the composition of the atmosphere to convert it, because all it gives you is a density profile. So you need to know the composition of the atmosphere to turn it into a temperature profile. But for Saturn, we did that pretty well.
Are the satellites always in an orbit beyond the rings?
Yes. It will have, it's running out of fuel in 2017. It will finally run out of fuel, and they've had a long debate as to what to do with it when it finally runs out of fuel, and they're basically just going to let it plunge into the atmosphere, and they're going to have a couple of final dramatic close-in orbits where they'll go through the ring plane, and they're hoping to do some great science as they go through, through the ring plane. Of course, they hope that they don't hit something that's going to terminate things prematurely, but most of the time we stay outside the rings for safety's sake as much as anything. Yeah, even the periapses are sometimes disturbingly close, and you worry that you're going to get into trouble. But by now, 8 years and 9 years, and almost 9 years into the mission, I think we're satisfied that the basic orbits are not too dangerous. All you need is to hit a little chunk of something, and then that's the end.
Can you show the zonal wind versus latitude one more time?
What would the rotation rate be if you integrated all those and the east and west added up? Like, what rotation rate would satisfy that?
So to get equal eastward and westward, it would only have to be different by about, I think it was like 6 minutes or so, something like that, to even things out. But not that much of a difference.
Okay, so 35 is kind of the terminus of the Equatorial Jet.
So yeah, that's right. Right. So their idea is that this Equatorial Jet is broad for a particular reason that has to do with the tangent latitude for the cylinders, for the deepest cylinder. But again, they don't physically have. I mean, they try to make up in their paper. They have a justification for why it should be at about 0.85 to 0.9 Saturn radii, but it's so much hand waving. Nobody really knows what's going on down deep, and when would the electromagnetic forces really terminate motion, and so on and so forth. No one really knows.
So don't you have this hexagonal thing at the pole? Is that
I left that out. Yeah, I mean,
so
actually both poles.
So the tubes wouldn't reach. They couldn't be sufficiently deep to
So
have anything to do with
right.
it.
So Booth's original idea was that actually the jets would stop at some latitude, and then poleward of that you wouldn't have jets at all. But that was in the 1970s when the high latitude just sort of looked kind of splotchy and not very organized to us. Now we know that there are jets that go right up into 80 plus degrees latitude, and so that's one of the reasons nobody takes Booth's original idea very seriously anymore, and why now they move these cylinders farther out and assume that there are other processes going on that can create alternating jets all the way up fairly close to the pole. But yeah, there are these hexagonal things that obviously represent some kind of a wave. Mike wrote a paper on one of those. He had to go to school. Mike Allison wrote a paper on that many years ago. Okay. Thanks everyone.